Hello, my name is Tea Žakula. It's a great pleasure to be here, and today I will talk about something I'm very passionate about, which are smart and sustainable buildings. Before I go into projects that we are currently working on, I would like to explain how it all became, how this topic became interesting to me. I was doing my PhD at MIT, and at that time I realized that things that sounded very logical are not always the best option. I was working on a very specific type of control called model predictive control. And before I explain what it is, I would like to explain how we cool our buildings today. Imagine it's a hot summer day, you come in your office building, and before you come in the building, someone turns on the air conditioning. And in the afternoon or evening, when you leave your building, someone will turn it off, which sounds very logical. We want to cool building when people are actually in the building. However, if you ask computer algorithm, what is the best optimal way to cool your building if you want to save energy or you want to save money, you give that computer algorithm all relevant parameters such as weather data now and weather forecast 24-hour ahead. You tell that artificial intelligence what is the situation in the grid now and 24 hours from now. Actually, the computer algorithm will tell you that the optimal way to cool your building is actually complete opposite of what we are doing today, which is to cool our building when people are not in the building during nighttime. And if you think about it, it somewhat makes sense because during nighttime, usually prices of electricity are much lower, but also outside temperature is lower, which means that you can operate your cooling equipment much more efficiently. In parallel to finishing my PhD, I also had the great, immense pleasure to meet one of the world's most renowned architects, Renzo Piano. And I was astonished by the way he applies sustainability in his design. And I asked him why he's this world-famous architect, why is he so interested in sustainability? And he said that he believes that 21st century will be in some way shaped by the sustainability, and that as an architect he wants to be current, he wants to be living in this time and maybe thinking in the future. And so he believes that his role as an architect is to take what mechanical engineers, electrical engineers, civil engineers are giving him as a technical solution and to make it poetic. And I thought that was so beautiful and profound that it actually stuck with me until this day. So I finished my PhD. I decided I want to go back to Croatia. I want to stay in academia, but I actually focused my work more toward the real life, to collaborate with architects and to help them make those poetic and beautiful buildings, to apply all those great technologies in reality. Motivation for my work are actually hard facts. It's the fact that we spend great amount of time indoors. So if you look at 1 year and you imagine you enter your building on January 1st, you are actually in the building or indoors until November 14, mid-November. Just small percentage of time we are in our car or outside, which sounds a bit depressing, but it's the fact. Also, buildings spend a great amount of energy. We consider cars to be very important when we talk about energy transition, but in reality, of the whole energy consumption in the world, 40% of energy is being used by buildings. Also, if we look at the European Union, buildings are responsible for about 36% of greenhouse gas emissions related then to, of course, climate changes. Also, what is even more remarkable that today, in 21st century, with all technologies available, we have buildings that are literally making us sick. It's called sick building syndrome. It's a building where occupants are sick due to reasons that cannot be contributed to any other parameter than to HVAC system not operating properly. Here I mean heating, cooling, and ventilation system. Actually, in the United States alone, the US Environmental Protection Agency estimates that about $60 billion annually is being lost due to the fact that workers are taking sick days. But additional $220 billion annually is being wasted due to the fact that workers are less productive. Also, this is a great document if you want to know more about buildings and energy in general, and it was published in 2009 as a part of Paris Agreement. There are several key messages that I'm showing here, but I would like to just focus on two. First, says that the building sector has the most potential for delivering significant and cost-effective greenhouse gas emission reductions. But even more remarkable is point number 3, which says that proven policies, technologies, and knowledge already exist to deliver deep cuts in building-related greenhouse gas emission reductions. That means that buildings are very important and that we already have technology and knowledge needed to make substantial improvements in that sector. So the question is, why is this not happening? Well, whether we want to admit it or not, energy sector and especially building industry are extremely conservative industries. They have this approach, business as usual. And this is just one graph demonstrating that. So this research was done by Boston Consulting Group, a great consulting company, in collaboration with MIT. And they actually asked leaders in different industries what do they think about artificial intelligence and importance of artificial intelligence for their particular field now, and what do they believe, how will that shape their industry 5 years from now. And from results, as you can see, energy industry being very skeptical about the importance and impact of artificial intelligence on their field, which is remarkable if we know of all the great possibilities that this new technology is bringing to us and benefits that we can achieve with that, especially for energy industry that is very, very diverse and complex. Anyways, because this business as usual approach, more and more countries are introducing different recommendations, policies, laws that are trying to change the status quo. Probably among most aggressive is European Union, and this is just one example of that. So starting this year, January 1st of this year, all new buildings in member states have to be nearly zero energy buildings. This means that we need to build buildings that have really, really low energy consumption, and that small energy consumption that we still need to use to provide comfortable conditions need to be in largest part covered by, or in large part covered by renewable energy. Also, because somewhat we exploit word smart today, everything is smart. You have a lot of buildings that claim to be smart, but they are not actually performing as we would like them to perform. European Commission published recently a document that is trying to quantify intelligence of a building. It's a first step in the right direction. It's called Smart Readiness Indicator, and it has a goal to achieve improvement in 3 main categories. First, user needs. Of course, we want people to be satisfied, healthy, productive. Energy savings. We want to achieve all those demands by using the least amount of energy or least amount of resources. And also, we want to help optimize grid. I will talk more about this third topic and why it is so important. We don't hear much about that these days still in the media, but it's definitely a topic we will hear much more about in the future. We have used this methodology. It was published just a few months ago, and we ask ourselves, if I have new office building and I put the most modern state-of-the-art control system in my building, something that I can find on a shelf today, what would be intelligence of my building? And this is a number that we got. It's 30%. So as we can see, it's far from what we would like to achieve, which is 100%, and there is still so much room for improvement. In our work, we usually use inspiration from nature or traditional architecture. And here I will show just 2 examples that I thought might be interesting to you. This is incredible little creature. It's called African termite, and it builds these huge mounds. They can be up to 12 meters high. The termite doesn't actually live inside those mounds. It actually lives below the ground. So inside the mound, it's this very complex set of ducts that you can see on the right-hand side visualized in white. And the purpose of that is to provide fresh air in lower part of the mound below the ground for termites, of course, to breed. But what is also important, eggs below the ground need relatively constant temperature to grow, which is very difficult to achieve if you live in desert, right? If you have high oscillations between day and night. So this little creature has excellent understanding of thermodynamics and fluid dynamics and uses these ducts to actually bring fresh air, but also to control temperature underneath the ground. This is a second example. It's a Great Mosque of the Jen in Africa. It uses very specific type of cooling called free cooling or night cooling. The idea is if you have cold outside air, why not use that air to remove the heat that has been accumulated in this building during daytime and to somehow pre-cool your building so you can have comfortable temperatures during daytime. So actually this building has, on top of the building there are holes, and on top of those holes are balls, and in the evening someone removes those balls to allow cold, fresh air from the outside to flush the heat that has been accumulated. It's using buoyancy-driven flow inside the building. And this is actually technology that we are trying to replicate in some of the examples, in modern examples that we are working on, of course now using more modern technology for automatization of windows and so on. And now in my last part of presentation, I would like to talk about some selected projects that I thought would be interesting, something that we're currently working on. When I came back to Croatia, I was very lucky to have the possibility of having living laboratory. For any researcher, it is very important to be able to test codes, simulations, assumptions in real life environment. This is a office building owned by Croatian Energy Company, and actually we used it to develop model predictive control, something I was doing for my PhD, tried to replicate it on a real building. And we actually did manage to control 5th floor of this building from our university computer in real time. So we would gather all the data, also forecast for next 24 hours, and then send optimal control sequence to this building each 15 minutes. This is a second living laboratory that we are currently working on. It's a building that will be built end of this year, beginning next year probably. And this is a project we are working on in collaboration with Technical School Ruđer Bošković here in Croatia. What is special about this building is actually building where we actually want to show that 1 + 1 doesn't have to be 2. We want to show that if you take great technologies that are already available to us, that are optimized on a component level, you put them in a building and you manage somehow to optimize them on a building level, you can achieve advancements, benefits that are much larger, much greater than the sum of the benefits of individual components. This project is funded by the European Commission, and I will tell you more detail about it. Here we want to, of course, have collaboration with industry, testing all these great technologies. We are planning to have education programs. So imagine someone who in the future will be operating smart buildings. That person has to be educated. They have to have a lot of knowledge that is additional to the knowledge that we have now. And also, of course, we are planning to work on research projects using this building as a living laboratory. Building will be about 1,800 square meters of multi-purpose spaces, mostly classrooms and laboratory spaces. It will have 3 types of heating cooling systems, 4 types of ventilation systems, 5 concepts of using renewable energy sources, more than 1,000 measurement points, which is huge number considering the size of this building. And it will also have open code building automation system, which will be a heart of this building. It will have a combination of mechanical ventilation and natural ventilation. And today I won't have time, unfortunately, to go into details of each specific technology. But what is important is that we are trying to cover with this building 90, or I would even say 95% of systems that you would find today around the world. Similarly, with heating and cooling systems, we will have hydronic radiant floor ceiling. Imagine in your floor or ceiling, you have pipes, and through those pipes you are running cold or hot water for heating or cooling. Also fan coil system that is predominantly used in non-commercial in commercial buildings, in office buildings, etc. And all air system that is predominantly used in the United States. We will also have 5 concepts of using renewable energy. You probably heard about photovoltaic panels, probably some of you heard about solar thermal, ground source heat pumps, air source heat pumps. If you haven't, I encourage you to look into those to inform. They're all very interesting technologies. But today I would like to mention more details about one that we don't hear, that we don't mention that often, which is passive cooling. It is precisely technology that I have mentioned being used on the Great Mosque of Dijon. The idea is to use cold outside air during night or even during daytime to passively cool your building, meaning without any mechanical equipment, without mechanical cooling system, without fans, etc. So this is just one example. If you can manage to operate building in such way, that means you have automated windows. Blue line here representing outside temperature. So you can see during night time being relatively low and then during daytime going up to 29 Celsius degrees. We open windows at 10 p.m. We close them around 6 a.m. And the red curve is what is happening in the building, what is happening in your room. And as you can see, temperature never goes above 25 Celsius degrees, which means that you can always achieve comfortable conditions without using mechanical cooling. Of course, you cannot use that in August or September August or July, where temperatures are really, really high. But in shoulder period, which is spring and autumn, you can definitely use this technology. We have designed this building to improve the possibility, the potential of using passive cooling, and the savings for cooling that we are expecting due to the fact that we have this technology is about 25%, which is remarkable considering that it's very low-key technology. Also, large number of measurement points. As I said before, we are measuring temperature in rooms, CO2, humidity, everything you can imagine is being measured in this building, but we also have a weather station outside the building that measures wind, sun, insulation, temperatures, and many different parameters. Heart of the system is an open code building automation system, which is very unusual because today, if you buy control system by any manufacturer, of course, they have some kind of control which is then locked inside of it's like black box for the user. Here we ask them to open that box. We want to see what is inside and we want to be able to change that. Not because we want to steal someone's technology, but because we want to help them improve their technology, to upgrade it so that we can use artificial intelligence to better operate our buildings. This is a design team that help us develop this building, to develop every single detail of systems that were important for us. And I will talk now about two important projects that will be happening on this building in terms of research. So first is related to COVID pandemic, because when this pandemic started, first, the World Health Organization said there are two main methods of transferring virus. First is through direct touch, so through contact, and second is through large droplets. Droplets, for example, when you're coughing or sneezing, those are droplets that are influenced by gravitation. But then, after a letter of many, many researchers, they acknowledge that there is a third mechanism that is equally or perhaps even more important, which is airborne, through very fine droplets in the air that are called aerosols. And because they are such fine droplets, they are not influenced by gravitation, which means they can spread to much longer distances. However, when the pandemic started, we didn't know much about how the ventilation system impacts that aerosol transmission, because we are not designing our ventilation system for the time of pandemic. We are designing it just to provide fresh air, and that's it. So today, we have solid evidence that aerosols are an important factor in spreading the disease. Also, that ventilation and filtration are effective methods in reducing risk of transmission. Unfortunately, there are many, many important things that we still don't know. For example, we don't know how different type of ventilation systems and how different rates of ventilation impact the transmission reduction, or how the air is being spread, how aerosols are being spread, how in the future to design ventilation system, having in mind that another pandemic might occur. And this is precisely what our group is currently working on. We are using a very complex type of analysis called computational fluid dynamics. Perhaps you have seen it. It's usually used in automotive industry and also in airplane industry. It's very complex, painful, but the results you can get with this method are extremely useful. Also, what is very, very useful on this building, what is remarkable, is that we have a building where we can actually test our assumptions and where we can test whether our simulations are correct, because we have designed one room in this new building specifically dedicated to test different type of ventilation systems and to test aerosol dispersion inside the room. Also, model predictive control that I mentioned before is also research that will be happening on this building, and it already started. So all the great algorithms that we have mentioned that we are now simulating and trying to predict how they will behave in a real building, we actually want to put them on the real building and see how the building will behave. There are thousands and thousands of papers that we can find in the literature showing that model predictive control has a great potential to make advancements in building industry. Unfortunately, what we still don't know and don't understand is how to apply something that we develop for one specific building to 10 buildings, 100 buildings, 1,000 million buildings, because each building is pretty unique, and there are many different obstacles that we need to overcome if we want to scale up this technology to thousands, millions different buildings. Also, what we are looking into is how people will communicate with artificial intelligence. People are the most important subject in a building. So we want to be able to get their feedback, we want to be able to optimize building based on their preferences, but of course people are at the beginning not so eager to give their feedback, to communicate with artificial intelligence and to actually communicate with something that at the beginning they definitely don't understand. So we are trying to see how to overcome some of the obstacles that come into play here. At the end, we want to achieve intelligence of this building from about 30% to something more than 90%. But the number is not important. What is important is all the cool stuff that we can do with this building. So I'm not sure how familiar you are, but today there are periods in electricity grid when prices of electricity are really low or even negative. That means that someone pays you to take electricity from the grid. This is happening because as we have more and more renewables in the grid, there are periods in a day or night where you have so much energy that you have more energy than you needed. And storage for energy today is a big issue. So we don't know how to store that energy. So someone is actually willing to pay you just to take energy from the grid. And this is a moment where buildings can have great benefits of using these situations. Also, we can do much more than that. We can improve the overall efficiency of a building, which means that we can reduce the overall energy consumption. We can do something that is called load shedding. So imagine a summer day, afternoon, 2-3 p.m., everyone AC is turned on. There is a huge peak in a grid that is a big obstacle, big issue for grid operator, and again, buildings can help shift that load when needed. Also, we can shift load from daytime to nighttime if that's what would be beneficial for the grid. And of course, someone, again, grid operator is willing to compensate building in terms of money or some other way to do so. This is a team that will be working on this. They're all part of Laboratory for Energy Efficiency that I'm head of. And under my mentorship, they will be working on these research topics and help us develop a great platform to test all these advanced technologies. Their names are Boruto Merzo, Arlinda Bresa, and Nicola Bajun, all PhD students. And with this, I would like to conclude. I hope it was an interesting presentation, that you learned something new. And if you have any questions, my email is here, so please feel free to contact me and share your thoughts. Thank you very much.